Assalamu alaikum. This is the second part of the guidelines. It's going to be a very short part. I just want to clarify a few things. So you remember when I talked about the correlation matrix and the correlation heat map? So this is the correlation matrix. So this Y is the target variable. So here, like for example, the correlation between Y and X1, which is high, 0.7, versus like for example, the correlation between Y and X3, it's very low. Okay. So here there are two things you need to look at: the correlation between each feature and the target variable. So the ones that are more correlated are the ones like uh, are the ones who you would keep if you want to remove some. Okay, so if you want to exclude some features, then you may need to exclude the ones that are weakly correlated. But also there is another thing that's important here, which is the correlation between the features themselves. Okay, if you have features that are very correlated to each other, then it means like there's a lot of redundancy here. So many features are telling you the same thing. So then there's a room here for dimensionality reduction or regularization, because you want every feature to tell you something different. Okay, so you don't want that redundancy. Therefore, if there is a lot of correlation between features, maybe then you need to eliminate some of them either manually or by regularization or by dimensionality reduction through PCA, or just manually removing some as well. Okay, that's one thing I wanted to mention. So in summary, so for the features, the more correlated to the output is the more that's the correlation with the output is good, but correlation between different features, many features are correlated, then there is redundancy here. Okay, so it's it's better if you are left off with the features that are less correlated to each other, but they are more correlated to the output. Okay, that's one thing I wanted to mention. The other thing was, let me remember. Yeah, when I talked here about like how you compute the error. Okay, so here is a slide here I added here. So this is actually when you are doing the model fitting or the training, then you are using this function for where the penalty function could be the norm 2 square for the ridge regression, or the norm 1 for the lasso. Okay, if it's just OLS, then lambda is equal to 0. This term is not there. So for lasso and ridge, when you train, you are using this function. Okay, but when you want to compute the training error after you train on the training data, okay, on the training data set, then you don't use this term. You just compute the error here. So that's the error you're going to look at. Okay, you do the same if you want to compute the error for the cross-validation data set. Here you compute the same error, but here you're using the cross-validation data set. And if you want to compute the error on the testing data set, you use the same term here, but you are using the testing data set. So yeah, these are the errors that you will look at, and you will actually you want to conclude, for example, if the training loss is very low, but the validation loss is high, then there's a problem of overfitting. Then you need to go back and do something with your regularization term. Okay, so you increase lambda, for example, or you may need to consider another penalty function if you have started with only one choice of them, for example. Okay, one final thing. Okay, I just remembered now. So here, remember for option 3, when we talked about like you can also build a model based in the principal components. So then you remember later on, for any sample you receive, okay, you need to perform that transformation using the parameters that you have computed when you performed the BCA, because for the principal components, each one of them is a weighted sum of the original features. So you need to keep those weights. So later on, if you have a new sample, okay, then you need to project it into the lower space, okay, using and produce the projection of that point into the lower space using those weights. And then after the dimensionality reduction, then you feed that sample to your model and you predict your output. And then if there is any normalization or whatever, then you need to actually reverse that operation. Okay, with that, I come to the end of explaining those guidelines. And I would like to thank you for watching. Salam alaikum.